Right, let us take a look at our example 3. And the example is from method of images. And what we have is two conducting planes which are 90 degrees to each other. These are very large planes. So think of conductors which are placed like that, coming in and out of the screen. We have just drawn a cross section through that. And we have placed a charge Q at that place. The question is asking you, where are the image charges which are going to be created? Well, part of the question is pretty straightforward. This bottom conductor or horizontal conductor would act like a mirror, and thus it would create an image charge exactly B behind it with opposite polarity to my charge. And similarly, the vertical conductor would act like another mirror and would create an image charge minus Q behind that. Is that it? Are these the only two image charges which are present? You may want to pause the video here and think through this before you continue. We have a problem. Let's say I want to go to some arbitrary point P over here and want to calculate the potential at that point. Then the charge plus Q and this charge minus Q, they are going to be the same distance away. And a potential due to these two charges, one is plus Q and other is minus Q. The potential due to those charges is going to be 0 at point P. That's how that image was working, right? Anywhere I go on the horizontal conductor, these two are going to combine and make sure that the potential anywhere on that middle section is 0. However, there is potential which is going to be created due to the second image charge we have put in. That is a different distance away, has a magnitude of its own, and thus, because of this image charge, which is created due to the reflection on the vertical plane, we are going to get a potential which is going to vary as I change the position P to different points on the horizontal plane. That is definitely going to be there. That has created an issue. And similarly, if I went to some other point P1 here, these two are going to cancel out, but this one is going to create a potential at that place. How can we get out of this? There must be another image charge which we have to think of. What if I put another reflection at the bottom corner over here? The problem is that, yes, let's go to the horizontal plane. Yes, this and this are combining to make the potential at the horizontal plane to be 0, but this one is creating a potential on the horizontal plane. Now if I put a charge plus Q, not minus Q, plus Q, this distance to my point P would still be R1. This and these two distances would be exactly the same. So what would now happen is these two will combine to make B is equal to 0 on the horizontal plane. Similarly, if we go to point P1, then these two will combine to cancel to make V0 on vertical plate. Now everything is working fine. Anywhere I go on my conductor, the potential on the conductor is equal to 0. So by creating these four image charges, removing the conductors which I have, by creating an image charge which is a minus q here, another image charge a minus q, and an image charge a plus q, we have been able to create the original problem. We have been able to recreate the original problem, the conditions of the original problem for potential at the boundary, and the condition is that the potential anywhere on these two planes has to be 0. This and this combine to make potential 0 here. This and this combine to make potential 0 here too. And similarly, this and this combine to make potential 0 on this surface, and this combine to make potential 0 on the vertical surface as such. So instead of solving the problem of two conductors and a point charge, we can now solve a problem to find electric field at any point due to the four charges which I have available. These are the image charges which would be created in this example.